polymethacrylates containing photocleavable groups for potential dental resins. And so the target of this project was to look at a dental resin that was similar to current dental resins, but have a photocleavable group in it, which essentially would, upon irradiation of light, would sever bonds and thus destroy the structural integrity of the material. So current dental resins are based on this molecule here called bis-GMA, and it's a bifunctional monomer containing a bisphenol A central group and dimethacrylate ends. And it undergoes radical chain polymerization to yield the bis-GMA resin. And it's applied to the tooth via an acid etching method. So acid is applied to the tooth, leaving a porous material behind on the tooth. And then the resin is applied and then cured with light. And so what we were interested in doing is developing a polymer that was similar to the structure of bis-GMA, but had the photocleavable group worked into it. And so we looked at the triazine group. And the triazine group has been used in monolithography and other as a photocleavable protecting group, so we knew that it could be used for photocleavage. And so what we did is we worked through the synthesis of our monomer. We studied the synthesis, the characteristics of the diol intermediate here because it's more stable than the dimethacrylate. And so what we looked at first was we wanted to see how it performed in the solution in solid state. And so we used IR spectroscopy and UV-vis spectroscopy to study the presence of the triazine unit. So here's the IR spectrum, and we can see that it has a diagnostic peak at around 1350. And the UV-vis spectrum has two peaks here, one around 290 and the other one at 325. And we studied this in the solution and solid state because we anticipated our final polymer to be insoluble. And so what we saw was that there were diagnostic peaks. And so then we took our diol intermediate, irradiated it with light for a given amount of time and in a given different amount of states. So we studied it as a pellet or as a tablet in solution. And we studied what it looked like after. So here's our spectrum before. We see our two diagnostic triazine peaks, and after there is no peak, which was exciting because photocleavage occurred. And we also saw this in the solution in solid state, and we saw it in the IR spectrum as well. And so once we understood how the triazine unit worked, we then polymerized our dimethacrylate using a radical chain polymerization, which was heat initiated, to yield our polymer. And this is our polymer here. The triazine unit is worked in as a crosslink with the dimethacrylate backbone. And this is the polymer structure for simplicity's sake. So then we took our polymer, we irradiated it with light, and we studied its photochemical properties. So we see our two diagnostic peaks before and after in the UV-vis spectroscopy at 290 and at 325. And then after photochemistry, there is no peak there. And we also see it again in the IR spectrum where there's the peak at around 1350 and then at 1350 after there's no peak. The final thing that we looked at was we wanted to see what would happen because upon irradiation of light, the triazine unit gives off molecular nitrogen. And so we studied the weight loss due to the loss of nitrogen gas. And we did see that for the different polymers that we made, there was weight loss observed, and so therefore we could determine that photocleavage had occurred. So where we're going with this project is we want to study different copolymers. We want to incorporate different monomers into the mixture and see how the properties change. And we're also interested in looking at a different monomer resin, which is similar to the one that we worked on here, but instead now it will have potential for hydrogen bonding. And also we want to look at other photocleavable groups such as an orthonitrophenol ether group. And we've started synthesis on both of these, but we need to polymerize and then study the photochemistry of them.